Welcome back, everyone. You join us for the final session today for the HydroGNSS webinar. The last session is a section on the use of data, followed by a roundtable user session. And the chairs for this session are Mirko Albani and Kimmo Roitinen. Mirko is the Heritage Space Program Manager from the European Space Agency, and Kimmo is the Senior Scientist in Earth Observation Research from the Finnish Meteorological Institute. Over to you.
Thank you, Ben. So we dive directly into the first presentation of this session. The presentation will be given by Estelle Cardeillac from the Institute of Space Science of Catalonia. Estelle has already made a presentation today, so we know her very well. And so I hand over directly the floor to you.
Thank you. I'll try once more to put in presentation mode, but no, it doesn't work. So I'll continue like this morning. What I would like to discuss with you this afternoon is about the MetaConRef study and the potential role in the future of one of such meta constellations. As you can see, the list of co-authors and organizations behind this study is quite long, and I'm going to give you more details in this talk. So we just saw today that HydroGNSS consists of 2 satellites, both of them with a GNSSR payload on board, and we've seen that it has unique characteristics, novel observables with capacity to unfold maybe new or improved products like dual frequency, dual polarization, multiple GNSS constellations, and also the use of a coherent channel. So yeah, we know that this have potential for high quality GNSSR products, but the truth is that HydroGNSS is not the only GNSSR mission, and that at the moment there are many other GNSSR missions into the orbit. So we can talk about the meta constellation of GNSSR missions. And here the questions that we might be interested in is which can be the contribution of this mission into this meta constellation of GNSSR satellites, and how can we leverage the different characteristics and performances of HydroGNSS and the rest of GNSSR missions for a common Earth observation goal. And also whether we can imagine HydroGNSS as part of a multilateral meta constellation, which would be the added value of this. Yeah. Part of these questions can be preliminary studies in this MetaConRef project, a collaboration. But I advance that in principle, HydroGNSS data will not be included, at least in this first edition of this cooperation project. So now I'm going to talk about this MetaConRef project. And the idea is that you have here a list of GNSSR missions that are currently into orbit with active satellites. We have 8 NASA, well, now 7 NASA Cygnus satellites, several Aspire Global Near-Nadir satellites, Monospace satellites, Fengyue 3, Mufeng 1A and B, Tianmu, Yunyao, UK.1, Triton, EOS 8, and also missions to be launched soon, like HydroGNSS, Amazonia 1B, and also the Atlantic constellation. So there are over 40 low Earth orbiters producing GNSSR data. And the idea is what we can learn from these dense meta missions of missions. And for that, we are conducting this MetaConRef study, meaning Meta Constellation of Reflectometers. This is a collaborative effort involving scientists and commercial and non-commercial GNSS reflectometry data providers, with the goal of showing the potential of a high-density GNSSR system, to which HydroGNSS will contribute soon. I have to say this is not a funded project, it's just a collaboration based on agreements between data providers so that they can share their data in a neutral and constructive way to investigate the objective of this study. Also, given the large amount of data produced by commercial companies compared to this total amount of data that we are talking about, it is important to highlight that this study does not aim at comparing different missions, and the results shall not analyze these aspects. The results of MetaConRef should always show blind measurements, as all different missions are here treated as a single one, as just one big meta constellation. And then we focus the efforts on the combined performance of them all only. We have a set of questions we will try to answer with this study. The scientific questions will be, what are the benefits of such a large GNSS satellite metaconstellation? How is the actual final spatio-temporal coverage and resolution? What scientific cases could be resolved with this density of measurements that cannot be properly monitored with the current Earth observation system? We also have, here, ideally, we would like to analyze the impact also of a simulation of this type of measurements into numerical weather prediction models or hydrological or any other operational system. But at the moment, we are not ready for that. So we will not consider any data simulation in this study. So we also have engineering questions, such as the challenges of such metaconstellation, how limiting are the factors, such as the differences in format, differences in instrumental parameters, how to do the intercalibration of the power measurements, the inhomogeneities in the way the different missions do quality control and uncertainty characterization. This can be quite challenging. And also, we wonder if we need to suggest further homogenization actions, especially for future missions, if we want to do a common use of all this diversity of systems. Then also some programmatic questions. What is the comparative cost benefit of such a multilateral system? And does the improvement in the performance justify the cost of incremental satellites? Can we issue recommendations for future GNSSR systems, optimal or minimum total size, intercalibration, harmonization, and so and so? Okay, the status of this study. We just started very recently. Here you have the list of participants and the different degree of involvement. Some are just observers, some will participate in intercalibration of level 1 and science, some are data providers. Every participant has chosen the role that fits better their availability and interest. So the first thing is to select a time window. We can pick 6 consecutive months, and preferably after February 24. And the reason of this date is because the Tianmu GNSSR constellation was completed by then with 22 GNSSR satellites. Yeah. The data is made available through the participants, and here we have a plot of how many satellites were active from each of the participants, data provider participants in the study. And in the top one is the total number of satellites. So we see an oscillation between 35 and 40, almost 40 satellites along this month. So we want to maximize the total number of available satellites, but also we would like to maximize the number of different missions involved. And well, the reason is to bring this challenge of inter-comparison and to check really the difficulties of harmonizing and putting together all these different technological solutions. And for that, maybe the here I marked in this calendar the different missions, not the number of satellites, just different missions a long time. And what we see is that starting in April 24, we have a lot of satellites we saw in the previous slide, but starting in September 24, we have a lot of also different missions. So we would pick one of these time windows, 6-month time windows. Another thing that is interesting is to make sure that during the time window we select, we have interesting science cases to check and to work with. And here we did just a compilation of things that happened during those months. That doesn't mean that we'll look at all of them, but at least to make sure that we can look at some of these interesting cases. For instance, there was a Hurricane Helene in September 24. It was a category 4 with 140 miles per hour sustained winds, landfall in Florida, 5 meters of storm surge and flooding across broad areas in North Carolina. So we could check floods, storm surge, altimetry maybe. There were also a South Fork fire in June 24 in New Mexico. This grew very rapidly. In just 24 hours, it burned 61 square kilometers. And here the challenge would be to detect and monitor a rapid fire increase in a small area. Can we do that with all these satellites? Some link, the livelihood assessment to relate pre-fire conditions to probability of fire. Can we say something about that with this amount of data? Another example would be a dike breach in China. That was in July 24. 48 square kilometers inundation, including several villages. And can we use this technique as a suitable tool for rapid acquisition of spatiotemporal information to support real-time disaster response? That was a question I found in one of the reports about this disaster. Yeah, they're wondering what kind of tool could be used to help in this respect. Again, here we could just try to map a flooding, but also water level monitoring. And other interesting cases, for instance, in Brazil, Caiapó territory in Amazonia, throughout 2024, there was a severe drought and also a lot of wildfires. There were more than almost 1,800 hotspots just in September alone in an area similar to Belgium. So this is a lot of small feeder fires. And maybe we could try to monitor these detailed fire maps, and also the severe drought. How can we could we contribute to this monitoring? And well, these were just examples. So the next step will be to do a level 1 intercalibration, because well, what we want to do at the end is to fuse all this data in a way or in another, and we want to do it in a way that maybe other third-party people, other people can also maybe in the future look at this data again, but that should be in a blind way. So we have to find a way to combine all this and in a blind way, yeah. So to avoid any mission comparison and so and so. And for the intercalibration, well, we have to do some data format homogenization. Maybe we have to consider some standardization features. There are many things that we can do. I have a few slides on that, but I think now maybe it's not the moment to go into details. There are different ways of doing this, and the different groups involved, they all will do what they consider best, and then we'll compare and we'll try to see either which is the best way, or maybe to fuse all these ways and that's the status at the moment. No much progress. We just kicked off in April, I think, so recently. As a summary, just to highlight these different missions, commercial and non-commercial, that provide large volume of GNSSR data, but never have been put together before. HydroGNSS is going to contribute to this in a way or in another in the near future. We want to analyze this data as if it were a single meta mission to help understanding the added value of having great amounts of GNSSR at great spatiotemporal density. Well, all the challenges because of the different hardware, intercalibration, data formats, quality assessment, etc., etc. This is a collaborative effort. And the type of questions we want to answer are scientific, of engineering, and programmatic nature. And we will have available 6 consecutive months in 2024 to begin with. And that will be up to 39 active satellites simultaneously and from at least 7 different missions. Well, and I think that's all. Thank you.
Thank you, Estelle. This interesting presentation. It seems that there is no questions online. Anyone? Yes.
It's the first time that this is to me. I mean, maybe my bad, my ignorance has always lead me to that. Okay. But it's the first time I heard about fire monitoring with reflectometer. Is it true? Is the first time that you are attempting something like that? And
no, I believe there have been some publications already.
Okay.
Yeah, I can search for them.
Is it fire or the precursor to fire? The condition.
Forest disturbance, I think, is probably what it's measuring.
I don't remember what has been done.
Yeah.
Yeah, I think it's more than. I think different people has looked at different aspects.
Yes.
We can cross-check this.
I think Emmanuel is asking.
Yes,
So please,
just to add that we did something, but is about forest disturbances, of course. At the band, we cannot detect the fire directly, but we can detect the status of vegetation before and after the event. So this is at least my experience. We published something on this in 2022, is to monitor the fires in Angola, in Central Africa, which was an area that has been heavily affected by fires during the summer 2022. So we attempted to find out the disturbances due to fires, and we found something.
Okay. So it's based more on time series of measurement.
Yeah,
Yes.
before and after changes in. Yeah.
I have one quick question. Of all these active satellites and missions, how many of them are able to provide measurements over high latitudes on land areas?
I think most of them, except Cygnus and maybe, I don't know if some of the Fengyu. No, I think Fengyu is polar as well. I would say if not all of them, most of them.
Okay, interesting to know. Thanks.
Thank you. So thank you, Estelle. And we move now perfectly in time to the next presentation. The next presenter is Sean Healy. Sean works at the European Centre for Medium Range Weather Forecast in Reading, UK. And he's a senior scientist and team leader in the Earth System Assimilation section. So Sean will present us activities on GNSSR impact studies. And say that, I leave the floor to you, Sean.
Thank you. Thank you very much for the introduction. So I'm going to just review some work that's started or is about to start at ECMWF, and it's composed of many co-authors, just a few listed here. Giovanna, Sale, myself, and Patricia has contributed to this talk. And there were also some input from NOC, in particular Giuseppe Forte, who's just left NOC, I think, Christian Buckingham, and Isadora Zampol. So the outline of my talk is to really just go over two ESA-funded studies in GNSSR. The first, I will briefly introduce the land study that's about to start on July the 1st, and that's led by Patricia. And then in slightly more detail, I'll go into the ongoing GNSSR ocean wind study that started in 2024. and is kind of about halfway through the project at the moment. I'll make a general point initially. One of the strategic actions of eSIMWF is to improve the use of new and existing observations. And then there's always a balance as to what proportion of our efforts go into the new and what proportion goes into existing. There's some mission experts feels, for instance, that we don't make enough of scats. We should be working harder on that. But we also try to contribute to the planning of the global observing system in terms of simulated observations, looking at the impact of them and assessing new data sets that might not be yet ready for operations. What I would say in that context is that the GNSSR progress at eSIMWF really has been limited because we tend to focus mostly on near real-time data or data that we expect to be available in near real time soon for operational assimilation. And just thinking back to my own experience in radio quotation, we were doing ESA projects in 1996 and we went operational with GPSRO in 2006. We do look at promising new data, in particular when we're supported by agencies, for instance, ESA or EUMETSAT. So ESA are the supporting agency in this particular case. So moving on to the new project that we're about to start in the land data assimilation at eSIMWF. As I said, it's led by Patricia. Estelle is involved and various co-authors both at eSIMWF and elsewhere. The motivation, we talk about Earth system approach in numerical weather prediction now. Historically, we've had various assimilation systems that have kind of grown up independently. And now increasingly, we're coupling the atmospheric data assimilation system to, for instance, the land surface DA system, to the ocean system, and so on. So our key aim is to try and improve the exploitation of observations, which we call interface observations. They're kind of sensitive often to more than one component of, say, the atmosphere or the surface. And within that context, the project at eSIMWF is to develop or explore the assimilation of GNSSR reflectivity over land and evaluate the impact both on the surface parameters and through the improved surface, the impact on NWP forecasts. And if we get it into operations, it potentially is useful for reanalysis going forward. It's a 2-year project starting in July, as I said, and it also has some kind of complementarity or synergy with a fellowship, early career fellowship, where we'll be looking at the direct simulation of level 3 soil moisture data. So this particular project, the ESA project, we're going to look at to try and do level 1, and we're going to assess the level 3 impact as part of this fellowship project. There you go. This is a slightly busy slide, but it gives you an idea of the kind of coupling of the DA systems going on. We'll have traditional SYNOP information that goes into what we call a 2-dimensional surface OI system that improves our temperature and humidity at the land surface. That is input into what we call EC land, which is also forced by atmospheric winds and is assimilating SMOS soil moisture information. The new bit we're putting in here is this kind of ability to assimilate the level 1 GNSSR information. So the level 1 is here in the red box, and the alternative approach is the level 3 soil moisture retrieval assimilation, and that goes into the EC land, and EC land is then coupled into our NWP forecast system. So that's the overall aim, is to essentially build a system where we're able to assimilate the GNSSR level 1 data over land, and then assess what the impact will be on NWP forecasts. As I said, that's about to start. Moving to the ocean wind speed project, which has been going now for about 1.5 years. The study was instigated, and I would say instigated, not just funded, by ESA. They said we would like to have a better understanding as what is the importance of value of these data sets. So the key question for us is, what is the impact of the wind speed information of the ocean, and whether we can potentially help in future data buys. We've done this kind of study before for our rate quotation, where we looked at commercial RO data, and we're able to assess whether this was useful for our NWP applications. We're testing the GNSSR data into two different NWP systems. There's the ECMWF one and also the Metavis one. At ECMWF, we'll be assimilating the sigma naught values, and the Metavis, they will assimilate the retrieved wind speed. I'm not going to discuss that here. So we're going to be using well-calibrated Cygnus data that's been provided by NOC as part of the study, and we're going to be running impact experiments for at least 3 months, and we will compare the impact with, for instance, SCAT. So we'll take SCAT in and out, compare the impact of adding GNSSR on top of SCAT. We'll also look at the qualitative SPIRE data during this period as well. Just some background, really. Something we kind of generally say about observations. The value of an observation for NWP applications is not absolute. It really depends on what we already know. This is kind of quite a high bar we have currently. So ECMWF will be running a 4D VAR system, which typically assimilates around 30 million pieces of information per day from around 100 satellites, including ambiguous vector winds from 4 SCATs. The 4D VAR system, the way I think about it, is it's essentially a very complicated least squares fit, where you are trying to fit millions and millions of observations. The form of the curve you're using to fit is from a model trajectory. And we typically run kind of a 12-hour simulation window in what's called long window 4D VAR, and also 6-hour windows to produce some of our forecasts. On the right-hand side, you see the kind of typical coverage from the SCATs we're currently operational with. So as we know, they're important observation type, although they don't necessarily always kind of look too important in some of the general forecast metrics. They come into their own when they're tropical cyclones. That's when people tend to look if there was a SCAT available in the vicinity and so on. So we have quite a good coverage from SCAT, and we are using a lot of data prior to GNSSR going in. How we use data sets? I take my approach really from John Ayer's work that's kind of described in his paper from 2020. Essentially, when you're assimilating data, there's always a compromise between what's called the complexity of the forward problem, what you want to assimilate, the quantity you want to assimilate, and whether you want to assimilate the rawer product you want to assimilate, the more complex the forward problem is. The compromise there is if you go to a less raw product, you introduce additional pre-processing steps that may introduce assumptions that aren't actually provided with the observation. They aren't really driven by the observations. They're provided by other information. So generally speaking, we tend not to assimilate level 2 retrieval so much in our system. I would say SCAT is an exception, which still needs some work in my view, because a level 2 retrieval is something that you observe plus something you assume. So we don't really want to assimilate the information that's being assumed, particularly if it's geophysical and it might be an assumption about a parameter that we're actually forecasting in the first place. So that's why we tend to go to level 1. But I would say that having level 2 retrievals is really useful for understanding the kind of physical relationships and the information content. So I wouldn't, I'm not trying to rule it out. It's just not the way we tend to use the data in NWP systems. This is just an example of the kind of data we've been provided by NOC. On the left-hand side is some of their sigma naught departures, sigma naught values as a function of wind speed. And on the right-hand side is corresponding NASA sigma naught as a function of wind speed for various different satellite vehicle numbers. And the essential point here is that the performance of the NOC data is very similar to the NASA. I think it's Science Data Record 3.2. I would say we told NOC we didn't want to be using data that had kind of been calibrated with NWP or reanalysis in any way. So that's been a kind of quite hard constraint on the data products that they've provided to us. Once we've got the data, How do we assimilate it? Well, to assimilate data, you need three. In my view, you need three things, although machine learning has complicated this or simplified the situation slightly. We need a forward model that maps from state space, winds, so on, to observation space. So we need something that goes from state space to observation space, which would be sigma naught in this case. We need a realistic estimate of the observation error covariance matrix. And we need a decent QC system so that we can spot sigma naught values that are not consistent with the R matrix that we're assuming. We are in the process of developing and testing a neural network-based forward operator to go from 10-meter wind speed or friction velocity, or the parameters are still being decided, to sigma naught. And this is really based on earlier work we did with SCAT, not SACT, SCAT sigma naught. And you can find what we did with SCAT sigma naught here in a report. What we did there was essentially with SCAT, we get 3 sigma naught values, a triplet, and the current approach is to take the triplet and invert it to get a U10 and a V10, but there is an ambiguity there. You get a pair of these wind vectors. So what instead we tried with SCAT was to assimilate the sigma naughts directly. So we would just assimilate all 3 sigma naughts and let the 4D var adjust the state. And that seemed to work, although it didn't beat the ambiguous vector approach. It was a proof of concept. It certainly works, but maybe not better than the U10 or V10 yet. But that's the basis for our work so far.
We have 4 minutes, Sean.
Yep.
4 minutes left.
Thank you. So we just, this is where we are with the training. This is just looking at standard deviations into correlation coefficients on the top and standard deviations on the bottom of our ability of our neural network forward operator to fit the observations using friction velocity, 10-meter wind speed in the middle, and 10-meter gusts. I have to refresh my memory as to precisely what the parameter there is. And these are the standard deviations, 1.66, say you can see here in dB, and this is just a correlation coefficient. I should say that these are lower value fits or higher errors than we got with the SCAT sigma naught, so that needs to be understood a bit better. But we are developing this forward operator, as I said. This just shows you kind of the gradient of the sigma naught with wind speed. You see the red line here. This is our fit. This is the gradient of sigma naught with wind speed from our neural network operator. What concerns me slightly with the GNSS R data is the applicable range of wind speeds where it's going to be useful. It seems to me to be quite a low sensitivity between above 15 meters per second, which is considerably below, say, 35 we use for ASCAT. I think I'll skip that. So we're going to continue to work on the machine learning forward operator, and we aim to be running simulation experiments this year. We'll be looking at some SPIRE data, and the Metaphys will be hopefully getting wind speed retrieval information later this year from NOC. So just to summarize, we have 2 projects going. The soil moisture study will start in July. The wind speed information study is ongoing. We're about midway through, I guess. I think the important point is that we don't have the capacity to try to test all data sets that are available out there, even if they're very good. We need to be supported by agencies or guided by agencies for priorities, like we were in this particular project. And I think we hope to be running the sigma naught experiments for the wind speed information later this year. And I think I can end there. Thank you very much.
Thank you, Sean, for this very interesting presentation. I don't see any. Oh, Cynthia has asked a question. We have been translating a signals-based algorithm for flood mapping to MOON and SPIRE data, and would be very exciting to use a merged larger data set and see the possibilities. Was this for previous actually?
Yeah.
Okay, it's just became
That's good,
during
because
this
I'm not sure I knew the answer to that one.
Okay, do we have any questions among the audience?
Yes, I asked you, Sean, in April in Leiden, but the possibility of including wave height in your machine learning forward model.
We could potentially do that. Well, it is a bit awkward because it wouldn't be available in the 4D VAR system. The problem with the wave height is that the wave height is so highly correlated with the wind speed anyway. So it might look better, but we're not convinced it really improves the system.
There's a question from Mauro.
Oh, why don't I see them?
Please just put his hand up.
Ah,
Okay.
Mauro,
Yes, I did both. My question, probably I missed this information, but my question is, which is the root mean square difference between the bistatic radar cross-section predicted by the machine learning, by the neural network, and the one measured by the GNSS reflectometer? I mean, the capability of the neural network to really reproduce the measured reflectivity or bistatic radar cross-section.
You want to see the plot again?
Yes, thank you.
Yep. Okay. So this would be the standard deviation of the fit during the validation. So if you're looking at it's actually standard deviation we're doing in dB, and that would be, this particular version is based on the friction velocity, and you can see the breakdown with regard to the Cygnus satellite number. So you can see that we're kind of somewhere between 1.65 dB or above, and you can see the correlations going above that. I should say for SCAT, I think we were more like 1.2 or 1.3 dB, so it seems to be quite a noisier fit to these observations than we were seeing with SCAT.
So is there any prior indication of what should be the capability of the forward model to reproduce the data? I mean, is there any requirements in terms of error in the forward model to get a good contribution to do numerical weather prediction, or can you say a number about this?
I honestly can't. I mean, we are essentially discovering these numbers right now, and I mean, if somebody has a forward operator out there that's not in machine learning based that is significantly better than what we're seeing, I mean, this will be a combination of forecast error as well as the because you'll be fitting to analysis or short range forecast information when we're trying to find the mathematical relationship. But we didn't have a kind of a number before we started this. We're actually trying to discover the number as we're going along. But if there are numbers, it would be really useful to know if you think there's a fit target we should be hitting.
Okay, I was just wondering whether it is understood which is, I mean, if the error is too much, probably this will not affect the forecast anymore. So if there is an idea about this.
Yeah, that's true. I mean, what I do remember is we haven't added noise to the wind speed yet. When we did something similar for SCAT, I think a 1 meter wind speed error would translate into about 1.2 dB or something like that. But we need to do that. But yes, you're right. I mean, if those, I mean, these departures, these errors look, so these RMS differences look quite big given the size of the signal for us. And I don't think it's a limitation of our forward operator yet, but if there is a better physical forward operator that can bring this down, we'd be interested to know about it.
Okay, thank you.
Thank you. That's a good question. Thank you. Appreciate that.
Okay. Yeah. My question was about getting back to Estelle's question about the wave height and also the fidelity of the forward model.
Yep.
So it's true that there's significant correlation between the wave height and the wind speed, but the component of variability in the wave height that isn't correlated with the wind speed explains, I think, it explains a fair amount of the variability in sigma naught that is not correlated with wind speed, because it affects the scattering. You know, the components of the C state or the components of the C state spectrum that are not forced directly by the local wind are explained, or a large component of their variance is explained by the C state components that aren't correlated with the wind speed. So adding the wave height to the forward as an input to the forward model, whether it's a neural net or a physically based model, I think will help explain more of the variability of sigma naught. And I suspect that some of that 1.6 dB of variability in your ability to explain sigma naught is because of that. That would be my guess.
That is certainly something we can test when we're building the forward operators. So we will go back to that. Yeah, that's a fair point. But yeah.
I mean, the fact that wave height and wind speed are correlated, even largely highly correlated, why does that make it not appropriate to include it in as an input to the forward model?
Well, the problem there is we'd almost be double counting. We'd have the significant wave height driven by the wind speed and the wind, so that going in, and then the wind speed going into the forward operator as well. I mean, I'm actually more concerned about the significant wave height going to retrievals than the forward operator, actually. But
right.
Because that to us is just forecast information that's already there.
Right. I mean, it's been our experience with Cygnus, you know, in developing the wind retrieval algorithm, that if you remove the component of significant wave height variability that's explained by wind speed, what's left explains quite a bit of the variability in sigma naught that isn't explained by the wind speed. So I think there's value in including that forward model.
Okay, but I mean, okay, so if let's say we've got 1.6 dB as the departures currently, so what do you think that would go down to? Do you have a feeling for that?
Well, actually, that number is highly dependent on wind speed. 1.6 dB is a very, very big number at 15 meters per second, and it's a pretty small number at 3 meters per second relative to the actual size of the scattering cross section. So I think it'll be highly dependent on, on the wind speed or on the value of sigma naught. So I think looking at what that error is as a function of sigma naught or as a function of wind speed is probably going to be informative about when it matters more or less. Also, the correlation between wave height and wind speed also varies with wind speed. I think there's weaker correlation at very low wind speeds because other things are forcing the C state when there's not a lot of wind. So how much of an impact it has, you know, the adding wave height to the forward model, how much that impact has will vary with wind speed because of the ability.
Okay, gentlemen, I'm sorry. I think we probably need to draw this discussion and have that discussion offline and come back to the agenda. Thank you very much.
That's fine. Thanks.
Thank you.
Okay, so let's introduce again the session with the final session for today, which is a roundtable discussion on exploiting HydroGNSS and GNSS are data for climate and numerical weather prediction. And I leave the floor to Estelle, who is facilitating this discussion. So
yeah, I'll try to facilitate in 25 minutes. First of all, I would like to introduce the panelists of this roundtable. First, we have Walter Dorigo, Head of Research Unit on Climate and Environmental Remote Sensing in Department of Geodesy and Geoinformation of the Technical University of Vienna. Hello, good afternoon.
Good afternoon, everyone.
We will have Mauro Pierdica, full professor at the Department of Information Engineering, Electronics and Telecommunications in Sapienza University of Rome. And Manuel Martinella, microwave engineer, principal engineer for Osmos Instrument, inventor of the Paris reflectometry concept in the European Space Agency. Hello, Manuel.
Good afternoon, everyone.
We can hear you, we cannot see you, but at least we can hear you. Chris Raff, Director, University of Michigan Space Institute, Principal Investigator of NASA's Cygnus mission in University of Michigan. Hello again, Chris.
Hi.
We also have Cynthia Zufada, retired Deputy Chief Scientist at NASA Jet Propulsion Lab. Hello, Cynthia.
Hello, Estelle.
Hello, we can hear you well. And finally, Martin Unwin, Principal GNSS Engineer at Surrey Satellite Technology. Hello, Martin. All right, so we won. I'll try to start this discussion with a set of questions. I think you'll need to be brief in your answers, otherwise we won't be able to go through all of them. And maybe the first answer could be answered to begin with by Mauro. And the question is, can you identify particular strength of HydroGNSS mission or GNSS reflectometry in general compared to other techniques?
Okay, I'm muting. Thank you, Estelle. And probably I could also summarize my short talk, putting together also the other question, that is, which is the strength and which is the weakness. For sure, the main strength is the fact that we have a small satellite. We can deploy many satellites with the cost of a single big mission, and this can strongly improve the capability and the visit of the observation of any of the product that GNSS can offer. So I think this is the main. And then also the fact that the type of observation that is carried out, that is bistatic near specular, is very much different from others. So I think that very important progress could be done by merging this type of observation with other type of observation. We did in the past some simulated work together also with Tor Vergata University, trying to put together backscatter and near specular. And since the mechanism of the scattering and the reflection are quite different, and they have different sensitivity to different target parameters, this may strongly improve the quality of the retrieval. So integration could be a very important topic to be investigated in the future, and HydroGNSS could help a lot. From the other side, probably the main weakness is the fact that the signal is very low. As I presented before, there is a strong capability of the right polarization, for instance, to provide independent and synergetic information for soil moisture, and probably for sure also for producing other quantity, other products. But the right polarize, the signal is very low. So I think that we could try to overcome this problem by improving some technology, especially the antenna, being able to deliver and to deploy beamforming antenna on a small satellite. This could really improve the capability of reflectometry if we are able to increase, say, by few dBs, 4 or 5 dBs, the gain of the antenna using a multi-beam or beamforming technique on the small satellite. I think that I have spent all my time, probably. So it's all from my side.
Thank you, Mauro. Maybe other panelists familiar with the technique. Chris, anything to add?
I guess I would maybe just kind of focus a little what Mauro had said. And I agree that one of the main benefits is the revisit time, and it's because the instruments are so cheap and they require very little power, so you can use a small satellite and so on. So it's possible to put many dozens of them in space. I think almost all of the things that they can measure, that GNSSR can measure, can be measured better by other much more expensive instruments. I think ocean winds and scatterometers is a good example of that. So the place you need to look at for the real unique contributions is things that change very quickly, because you're never going to have dozens of scatterometers in low Earth orbit. So things that change very quickly, like, extreme weather events or floods or, rapid intensification of a storm, things like that, are the things that a scatterometer won't be able to measure because they change too quickly. I think that another sensor that can measure very quickly is something in GEO. So an important distinction with GNSSR is to identify things that GNSSR can measure that can't be measured from GEO with optical or thermal infrared, things like that. And examples of that are things that happen at night or things that happen under heavy vegetation or under clouds. And GNSSR can measure a number of things there, like inland water, under clouds, and under vegetation, which you'll never be able to measure from GEO, even though it can measure with 5-minute revisit time. So I think looking at the differences between what it measures and what other things measure, and identifying, the distinguishing properties that can't be met by the other sensors is a good way to focus on the real value.
Thank you, Chris. Cindy, I don't know if you have anything to add to this list.
No, thank you. Not at this point.
Good. Manuel?
Yeah, I think one of the strengths is the spatial resolution for soil moisture. Can you hear me?
Yeah.
Yes.
And can you see me?
Yeah.
Yep. We can see you too.
Wonderful. Yes. You look wonderful, Manuel.
Okay, thank you. Yeah, so I mean, with SMOS, SMAP, CMAR, we know the difficulties in getting high spatial resolution soil moisture observations. So here is where GNSSR has a strength. But I would like to point out this as something particular for generally.
Yes, this is a good point. Yeah, thank you,
Yeah.
Manuel.
And generally, the large amount of observations possible by GNSSR and the great variety of applications at the model.
Yeah, this is also a good point. We'll continue with the next question. Maybe Cynthia, you can attempt to answer these questions. What are the challenges faced in using GNSSR measurements, and how could they be addressed?
Right. So the challenges, of course, are in principle this is a question that depends on who we are talking about. Let's say these are relatively easy data to work with, and this is probably something that could go into the list of benefits of the technique, right? Compared to other sensors that are a lot more complicated, so to speak, and so there are many more subtleties in terms of describing and treating the data and operating with the data. I'm just thinking to the complexity of SAR, for example, because of the maturity of a technique and the sophistication that a more complicated technique allows for, right? This being said, it means that there is an opportunity, because which has always been appealing in this community, and the opportunity is that it's easier to bring into the fold the newer generations of students and graduates and researchers relatively easily and quickly. So these are all good things in terms of the ability to access the data and learn how to use it efficiently and and successfully eventually for to answer scientific questions. At the same time, the community at large is still not necessarily aware of the reflectometry data. It's still a niche, in part because it's still a technology, right, that is upcoming, even after all these decades of research and then a long-going NASA mission, as well as upcoming actors in the new space. So perhaps these are, the two points that could be used as pillars in describing what's easy, what's difficult, and areas to still work on.
Thank you, Cynthia. Any other ideas for the challenges faced in this technique? Anyone wants to?
I can say a few things. I think that there's some challenges in some of the details with processing signals. There are subtle differences between GPS L1 and Galileo E1. There's differences depending on how you integrate them. So I think these could be benefits and challenges at the same time. It may make data a bit harder to make match with other data types. So I think that people just need to understand it better, because there may be benefits from different integration times, but it also may introduce some subtleties. But I think something that is a genuine challenge is going to be the RF interference. We already know it is. We see that with Cygnus, that there are some strong emissions from certain geopolitical hotspots in the GNSS bands. We will have the L5 on HydroGNSS, which is likely to have different kind of interferers, but interference is something we have to learn to live with and learn to mitigate as best as we can. And there's various ideas about doing that, but that's the challenges that I see.
Thank you, Martin. Any other ideas on the challenging aspects?
I have one.
Maybe
I have one.
Yes.
I think one of the hardest things that I've found in kind of marketing the Cygnus data products over the years has been because of the way the sampling works and the fact that we don't have gap-free wide swath imagery, which is what people are very used to. Many user application, users are used to that sort of data, but we have inherently gaps in our data, often lots of gaps when there's only one or two or a few satellites passing over a target area. And it makes it hard for users to adapt to this type of sampling. And also it's, just in terms of public relations, it's hard to make pretty pictures with these because of the gaps. And I think that's the most, for me, the most exciting thing about this new meta constellation that Estelle is leading is the fact that with 39 satellites, we're going to be able to make nearly gap-free images. And I think that's going to make this product a lot easier for people to understand and work with.
Any other ideas, or should we? Oh, okay. Walter, please. We don't hear you.
I'm not an experienced user.
You're back.
I'm so muted. Really?
Yes, now we hear you.
I'm not talking as a user of the data or as an expert of the data. Actually, even though I'm from TU Vienna, I haven't been involved in HydroGNSS so far. But I might be a potential future user of HydroGNSS or GNSS data in general. And we're looking now to my background. I'm science lead of the ESA CCI soil moisture project, and also responsible for soil moisture within the Copernicus climate change series. And what we do there is, Wolfgang Wagner has shown a similar slide in the beginning, is that we merge multiple satellites to get a consistent, as much consistent as possible long-term data set, which currently covers about 45 years, has a 25-degree resolution. We've moved to 10-kilometer resolution, a daily sampling, moving towards a sub-daily sampling, 6 or 12 hours. I was a bit skeptic in the beginning, what we could gain from HydroGNSS, and I think the potential really lies in the combination of multiple missions, as also emphasized in the previous talk by the Meta-ComRef initiative. So I think, and that also relates to what Chris Roth has said before, if we want to have gap-free data, if we really want to increase the spatial resolution, I would think it would make very much sense to combine data sets. I think two satellites are not going to improve the CCI soil moisture product. Maybe we gain some new insights. And another thing is that has been mentioned in the very beginning is that there may be a failure of one of the L-band satellites that we use, that we have to rely on, most above all satellites SMAP, but also SMOS, and in the future SIMA. They may overlap, SMOS SMAP versus SIMA. There may be a continuation L-band, but I see a potential, if this does not happen, there are still a couple of years to go. We may use, for example, GNSS R as a calibration target, for example, to match the L-band frequencies. Even though the L-band is slightly different, even though the frequency is slightly different, that may be a potential. So at the same time, I see potential and also maybe some caveats that still need to be bridged before we can really the users really fully take up the data sets.
Thank you.
Thank you.
Any other ideas on these challenges?
I think if we compare passive and active instruments for soil moisture retrieval, I'm of the opinion that passive instruments are more accurate. So we have to validate, for example, missions like HydroGNSS with SMOS and SMAP. Hopefully there will be an overlap. This is another challenge to really validate the accuracy of the soil moisture products of HydroGNSS and in general reflectometry.
Estelle?
Yes,
okay.
Mauro?
I would like just to add an example of how the GNSS reflectometry data do not provide a good picture. That is, have characteristics which are not common to other systems. So we had a couple of discussions with a group led by Wouter that has developed a system for validating soil moisture products. And we found out that Wouter, as a user, was not really aware of the characteristic of the product. So that type of validation tool that was mainly looking into the temporal variation of soil moisture was not suitable for GNSS reflectometry, since we have not a repeated observation over a certain point on the Earth, but we have rather a scattered set of points, of specular points during one day. So this was an example of this, let's say, difficulty in understanding the characteristic of the GNSS reflectometry with respect to other instruments. Just a comment. I don't know if Wouter want to add something, but I hope we will finally be able to have a better exchange and to include also HydroGNSS among the possible data product that could be included and injected into this calibration validation tool.
Mm-hmm.
We have 5 minutes left and the question.
Yeah, okay. We have not a lot of time at the moment. I believe that the third question that we prepare maybe has been already answered somehow. Maybe Wouter can add something else about these particular opportunities in the user domain, very briefly.
Yeah, I think apart from what I said before, on the use of GNSS soil moisture within a climate perspective, long-term climate data records, of course, there's also the long-term aspect that needs to be considered if you want to do climate research. What I do also see as a strength maybe is that we could further exploit, for example, what the impact of water bodies is on the soil moisture retrievals from radiometers or scatterometers, as they do significantly impact the quality of the retrievals. So, and often for smaller water bodies, we don't know if they're there. We don't see that as at a footprint of 25 kilometer or even closer. So maybe there's also some potential in there that we better understand the retrieval. We can actually optimize the retrievals from radiometers and even scatterometers. So that's one.
All right. So that then let's move to maybe, yeah, the fourth question. How could different GNSS reflectometry missions collaborate together for the common good? Benefits, challenges, how to do that? And maybe we can also link it with the last question, that if we want a future service to be sustained, that could be using commercial satellites. But if this is not possible, how could we do that? So let's try to, because we have not a lot of time, so any ideas on these two questions will be welcome. Cynthia, you have your hand raised. Please go ahead.
Yeah, my hand was raised from a previous discussion, and I just wanted to spend 30 seconds in terms of, there are substantial differences that are, in a sense, intrinsic to the measurement type here that are hard to understand for the community. The discussion here might give the impression that it's a problem of people not being used to seeing gaps, for example, in the data. I sort of, take a little bit of an issue. The problem is that we do not measure, the technique does not measure the same thing as, physically it is commonly understood. So the real reason for what remains some skepticism in the community is that is one really of interpretation. The fact that we are not dealing with an imaging system, and yet we are comparing sometimes this measurement with what an imaging system produced. So something that looks at the same thing in the same fashion over and over is very different from a system of measurement where there is an accrual and where the revisit is a concept that is, very, very relative. So that's something that, in my opinion, we should keep in mind in the discussion, because it's an exercise for us, the reflectometry community, to constantly engage with the others in a manner that it's still not too common, right? It doesn't happen, because very often we find ourselves at tables like this where the voices tend to be very uniform in this respect, to have that conversation. This being said, and very quickly to this last question, I think it's an excellent opportunity. The reflectometry is a technique that can be added, right? Because you have basically, as technique and technologies, something that are very consistent, so they can produce, waves of different receivers, different classes, even different generations of sources can somehow be integrated with ease. Again, compared to other technologies, and we can indeed expect that there will be constellations that are constantly replenishing and constantly adding for the benefits of the overall community, right? Because of moderate costs and low barriers to entry into these opportunities from universities and new companies. I'll stop here.
Thank you, Cynthia. We have 1 minute left. Anyone else wants to?
If we need a bit more time, I don't know if there's a strong deadline after this. I find it a bit. I would like to allow some time for this discussion. We have the right people around the table. It's the purpose of the day. So if we can accommodate 5, 10, 15 minutes more, if it's acceptable for everyone, I think we should do it. We should not put the pressure on time at this.
5 minutes left in the meeting.
Don't just ignore this.
Yeah. I think that there may be some. I'm not sure that there are significant issues in going over. It's possible that our Teams meeting will suddenly stop broadcasting, but we can try.
We might be able to look at extending the meeting in the background so we can avoid technical issues.
Yeah, would be good.
Yes, it's already doing something strange with our video in this room. But there's a voice coming through. That's okay. Yeah. So we can carry on for a bit.
It's just on our PC screens. It's fine.
Yeah. Okay.
So I had a comment to kind of build on something that Cinzia had said earlier about the ease of entry to spaceborne mission of GNSSR. It's, by far, it's so much cheaper and easier to implement than most other, high quality remote sensing techniques, because it's, the hardware is simple, the data rates are simple, the power is low, the weight is low, all these things. And I think that, even if you look at how it's spreading now, there's, so many new players that are flying GNSSR instruments, and in the future that could grow. It's a really good entryway for, smaller countries developing new space agencies, or educational missions, or private companies flying small, cheap satellites with low initial investment. I mean, there's a lot of opportunity there. And also there's, the ability to just buy a sensor that works well. And I think that the SSTL model is great for that. We couldn't have done what we did with Cygnus if there wasn't already a GNSSR sensor, mature sensor available just off the shelf, essentially, from SSTL. And something similar is happening now, I think, with Brazil also. I mean, they're going to have a mission, and they don't have all the initial investment in intellectual property development to get the sensor to work right. They can just buy one. And I could see this sort of thing spreading and having a lot more sources of GNSSR missions, educational, private, and smaller countries, space agencies. And then I think the meta constellation thing becomes even more important if we have a lot of these different things up there, and we come up with a good, reasonable way to consolidate all those sensors and data products into a common collected product with essentially no gaps and fantastic revisit times. I think that's a great enabler for the future of GNSSR.
But maybe then we would need a better standardization of, so we know that there are already some standards, but they are very basic, and maybe it would be better to consider how things could be done in a way that data and instruments are more homogenized across different missions.
I mean, for example, in between SMOS and SMAP, we have calibrated brightness temperatures, and then we have a regression, and that gives us just a straight line to convert brightness temperature from SMOS to SMAP and vice versa. In GNSSR, we could have DDMs shared among different satellites, different missions, and then maybe this kind of simple regression, even if every DDM is calibrated through whatever owner of that particular satellite is, to have a common somehow a common product that can be then used for all satellites. So there's an intercalibration problem to be solved, and also standardization of what products to share, to put in common. Yeah.
It's, okay, a comment from me towards trying to move towards a future standard, and I agree with standardization. I think there are forces that push against that, unfortunately, in that when you're working with space agencies, there's generally a need to do things differently, to do things better, or to add things, and so there is a pressure to always make improvements, whereas standardization is trying to make things the same. And so that there's always going to be a slight tension in that sense, but I'm sure we can manage it. I think one of the key ways that we need the things that need to happen is that the users need to take more of a role. If you look at the radio occultation, that's where it went. It's the people like ECMWF and UMETSAT, NOAA, and WMO start setting requirements, taking an interest, then that sort of helped kick the whole thing off with both institutional and commercial suppliers. And something similar, perhaps it would be good to see that, which try and encourage the users like the CCI for climate records, as well as the likes of ECMWF and Sean and UMETSAT and NOAA, to encourage them to recognize what the value of these measurements are. Then that helps with the user pull. It helps bring some focus for either commercial or institutional missions to provide a contribution towards that. I think encouraging, as Chris says, smaller space countries, this is a way that they could genuinely contribute towards the WMO or towards climate records. Then that would help provide the impetus for this to continue. But there is always the risk when you do an innovative satellite that is designed to have a 5-year mission. Then at the end of the 5 years, that's it. It finishes. I guess the other European force that's very relevant is Copernicus, that is pulling towards longer-term measurements. So if we can find ways that we can find parameters that can be measured, that we need these long-term, then that can be identified. It will help with roadmaps for the future.
Thank you, Martin. Any other ideas?
I agree that Copernicus is a good path for the long run. Yes.
Estelle, from my side, unfortunately, just a concern about point D, that is putting together different mission. I think that this can work quite easily for over ocean, because we are considering the sigma naught, the bistatic radar cross section, for a signal which is, I would say, for sure, incoherent. So this parameter should be independent from the geometry and the distance, for instance, the altitude of the satellite. But as for land, where we are mainly considering reflectivity, which is really an equivalent to reflectivity, it's not really a Fresnel reflectivity. This parameter is quite dependent on the geometry, for instance, the height of the satellite, the signal, the type of signal. So I think that it is a challenging task, try to merging different satellites with different altitude using different signals when we are looking at the land, especially because of the topography that changes the real, let's say, area of the surface on ground that is really contributed to the signal. But okay, I think that we will find a solution for this.
Mauro, do you think we could try to define an observable that is a bit like equivalent, let's say, nadir equivalent at this altitude, at 500 kilometers? If there are things that can be projected or mapped into different geometry or different height, because we know physically how this should be, then maybe we could define an equivalent and also do all the comparisons with an equivalent observable. Maybe this is something we could consider.
This is the target, of course. I don't know how to reach this solution, this target. But okay, that's the final goal. Will be having just one single observable, but there are many parameters that are affecting the observable, so it is not easy. I mean, we will try.
I have a question for Chris, and it's related to something that Manuel mentioned about intercalibration or making sure that one mission can be used to calibrate the others. Any chances that when HydroGNSS will be launched, Cygnus will be operating? Do we know if there will be any overlap or not?
So we live in very uncertain times, especially in Washington, and it's not clear whether I've been asked by NASA to prepare plans to turn off the satellites on October 1st, 2025. And we've done that, detailed plans. And it's not clear whether we'll need to implement those plans or not. It's very unclear because of the situation with the federal budget. So there's a possibility they won't overlap. Nobody wants to do this at NASA, but they may have to.
And if I can add, this is a really.
I think you should ask.
Sorry.
You should ask them to wait for HydroGNSS for the sake of intercalibration and time series.
No, I'm sure that will convince the White House. Yeah, that's a good idea.
It could be among the topic to discuss at the next G7 meeting, probably, because it would be really a problem, because we have trained our algorithm using Cygnus. So it is very important that the observable from HydroGNSS is comparable with the observable from Cygnus, or at least we can find a linear regression, for instance, as Manuel said, to convert one to the other. If we have not any possibility to have, let's say, common observation, at least for a few months, it would be a problem. Yes, in my view.
I agree with that. I think following up on what you said earlier, Mauro, about the difference between land and ocean. I mean, one thing that we've seen clearly in the ocean data with Cygnus is that there's a number of statistical properties of the measurements, the PDF and the CDF and the median, a whole bunch of things about the sigma naught over the ocean that are very stable from year to year. Stationary statistical properties. not so much with reflectivity over land because things change much more, but you know, because we have almost 9 years of data with Cygnus, the statistical properties of ocean sigma naught are very stable and stationary, and those properties could be looked at with HydroGNSS over the ocean as a form of intercalibration, even if Cygnus isn't flying.
We take a note on that.
I think we're going to have to wrap up soon.
Yeah. Thank you very much for all your ideas. Cynthia, is there anything else you want to add?
Just one last, is there anybody showing up and clamoring to pick up, perhaps a commercial operator, pick up what might be a reduced scope Cygnus operation if NASA shuts down? Are there any attempts to identify a sponsor, commercial sponsor that might pick it up?
Yeah, there's several attempts that are happening right now. This is what I'm spending most of my time on, and this is not perfect forum for me to discuss them right now.
Okay.
But yes,
we wish you well. We wish you well.
I'm trying very hard. I'm trying very hard.
Yeah.
Also, I'll just mention one thing, Martin. You mentioned RFI as a problem. In this case, actually, this is helping. The fact that we can measure it so well is helping.
Okay.
Good luck. All right. Good luck.
Okay, so I think we can close here the roundtable, and we can conclude this session.
Yeah, just see that there is a question on the chat. I don't know if we want to
I can answer that. So you said in Canada, yes, we don't have a product over lakes, but we know that we know some people in Canada who are very becoming experts on this, and we very much hope you'll be using data from HydroGNSS to and yes, we'd love to talk to you about in the future potential products for lake ice. So keep doing the good work.
Okay, right. Well, we'd like to stop there. I'd like to thank all the panelists and the co-chairs for doing a wonderful job. It's a fascinating session. And as we're over time, I won't spend too long summarising. I think what we'll say is it's been a fantastic day. Been handling some fantastic, really interesting discussions, beamforming, looking for things that where HydroGNSS and GNSS reflectometry can really make a difference. Very interesting to hear about the perspectives on the users and where things could go next. So with that, I think we'll close for the day. What I'll say is that the next opportunity to engage with HydroGNSS will be at the Living Planet symposium in Vienna. There will be an ESA Scout session on the Friday, I believe.
Yes, 2:30.
At 2:30 on the Friday. The SSTL team will be there, as will many of our scientific partners, and we hope to see you all there. So with that, I'll say thanks very much to everyone. Thanks to all the participants and everyone for joining.
And thank you to SSTL for hosting the event, and also I'm quite impressed by the interest from all parties, and that's quite good to at least we know what we are doing is to serve the community. So and I'm pleased to see the interest, and thank you very much for that, and also the good ideas and the proposals for improvements. And no, thank you very much. That's quite good, and it gives us another reason to wake up sometimes very early in the morning to make this happen. Thank you, everyone.
And thanks to ESA for great participation in the event today. It's wonderful.
We were not given a choice in a way.
All right. And I have my thanks too. Thanks to everyone for joining. Thanks to the roundtable. Thanks to all the presenters, and thanks for all the participants. We will endeavour to put the video up on the web at some point, accessible, so everyone can see this again.
Thank you.
Right. Thank you.
Thank you. Goodbye.
End the event.
Bye.